To dive into the analysis of air and water vapor mixtures, we've got to look at least three parameters. That's a bit different from working with a thermodynamic table for a single substance, where just two parameters usually do the trick. Why the difference? Well, in psychrometrics, we're dealing with a mix of two components, air and water vapor. That extra complexity means we need more information to fully understand what's going on. The psychrometric chart is built on the water phase diagram, specifically the line that separates liquid from vapor. If we zoom in on this phase diagram, we can see the saturation line, which divides the two phases and serves as the foundation for the psychrometric chart. In this video, I'm going to show you how to use this chart to figure out ambient conditions based on the local temperature and humidity. We'll break it all down, going through each parameter step by step. On the psychrometric chart, the x-axis represents the dry bulb temperature, which is simply the air temperature you measure with a regular thermometer. The y-axis represents the humidity ratio. This is different from the water phase diagram, where the y-axis shows water vapor pressure instead. The humidity ratio is the mass of water vapor in a given volume of air, divided by the mass of dry air in the same volume. Now, if we think of both dry air and water vapor as ideal gases, we can come up with an equation that links the pressure of water vapor to its partial pressure. That's actually why the psychrometric chart often uses the humidity ratio. It's directly tied to the partial pressure of the water vapor. It's also important to understand that each psychrometric chart is created for a specific total pressure. Now let's revisit the chart. You'll notice that the humidity ratio represents the mass of water vapor relative to the mass of dry air. Because of that, all the properties on the psychrometric chart, like enthalpy, which you usually see per unit of mass in thermodynamic tables, are calculated per kilogram of dry air. Now let's talk about the concept of the dew point. On the chart, for any given dry bulb temperature and humidity ratio, there is a corresponding dew point. This point lies along the liquid vapor saturation line, the place where the air is fully saturated with water vapor. Let's explore a scenario on the psychrometric chart where the water vapor partial pressure remains constant while the temperature decreases. At this point, we can trace the conditions to the saturation line, which marks the dew point. The dew point temperature is the point where the water vapor in the air becomes fully saturated. If you add more water vapor after this, or if the temperature drops below this level, condensation kicks in. In other words, the water vapor turns back into liquid form. Now let's talk about relative humidity and how it shows up on the psychrometric chart. Relative humidity is basically a measure of how much water vapor is in the air compared to the maximum it can hold before condensation happens. For example, if the relative humidity is 50%, that means the air is holding half of the water vapor it's capable of holding at that temperature. As more water vapor is added, the relative humidity rises. When the air reaches 100% relative humidity, it can no longer hold any more moisture, and condensation begins. The relative humidity is calculated based on the ratio of the water vapor's partial pressure to the saturation pressure of water vapor at the same temperature. Back on the psychrometric chart, relative humidity shows how close or far a point is from the saturation line or dew point at any given temperature. This distance visually represents how much more moisture the air can hold before reaching saturation. The specific volume displayed on the chart refers to the volume occupied by water vapor per kilogram of dry air. This property is important in determining air density and is used in various calculations related to airflow and ventilation. Using the humidity ratio and considering air as an ideal gas, we can calculate the specific volume with a simple equation. Let's dive into the concept of enthalpy of air and how it's shown on the psychrometric chart. The enthalpy of air is the sum of the enthalpies of its two main components, dry air and water vapor. Let's start with dry air. The specific heat at constant pressure, or Cp, is calculated from the change in enthalpy with respect to temperature. To make things simpler, we often pick 0 degrees Celsius as our reference temperature. In practical thermodynamics and HVAC applications, we assume the enthalpy of dry air is 0 at 0 degrees Celsius for simplicity. From there, the enthalpy is simply the product of specific heat and temperature. According to Moran and Shapiro's thermodynamics book, we can derive the specific heat for ideal gases using an equation that works for temperatures ranging from 300 to 1000 Kelvin. For dry air, a typical reference value is 1 kilojoule per Kelvin. The specific heat value doesn't change between Celsius and Kelvin, which makes things pretty convenient. Next, let's move on to water vapor. We calculate the enthalpy of water vapor in the same way as dry air. However, even though we eliminated the reference temperature, we still need to include the reference enthalpy. This reference is the enthalpy of saturated water vapor at 0 degrees Celsius. Since the enthalpy of water vapor is measured in joules per kilogram, we multiply it by the humidity ratio to express it in joules per kilogram of dry air. Now, coming back to the enthalpy of moist air. Once we know the enthalpies of both dry air and water vapor, we can calculate the total enthalpy of humid air for any given condition. Finally, let's break down sensible and latent enthalpy. The change in enthalpy between two states is made up of these two components. Sensible enthalpy is linked to temperature changes and depends on the mean specific heat capacity of moist air. Latent enthalpy, on the other hand, relates to changes in the humidity ratio and depends on the mean enthalpy of water vapor. On the psychrometric chart, a change in sensible enthalpy appears as a horizontal line, while a change in latent enthalpy shows up as a vertical line. So, if a process only involves sensible heat, the enthalpy change is purely horizontal. Next, let's explore the concept of wet bulb temperature and how it fits into the psychrometric chart. The wet bulb temperature is defined as the temperature of a parcel of air that's cooled to saturation by the evaporation of water into it. On the saturation line, the wet bulb temperature is the same as the dry bulb temperature. To understand this better, let's imagine an adiabatic saturator. In this ideal device, we have an infinite water supply at point 3. The mass flow rate of water vapor at point 2 is the sum of the flow rates from point 1 and point 3. In simpler terms, some of the water from point 3 evaporates, mixing with the air from point 1 as it moves from the lowest water vapor partial pressure at point 3 to the highest at point 1. However, for the water at point 3 to evaporate, it must absorb latent heat from the remaining water. As this happens, the liquid water cools down to the wet bulb temperature. So, the wet bulb temperature is a way to measure how cool the air can get when water evaporates into it. This process is called evaporative cooling. Under ideal conditions, the air at the outlet, point 2, reaches the same temperature as the water, which is the thermodynamic wet bulb temperature of the air. Now, using an energy balance, we can calculate the wet bulb temperature using this equation. Now, let's talk about the sensible heat ratio. The sensible heat ratio is the ratio of sensible heat to the total heat, both sensible and latent, added or extracted from a specific point. Imagine a room where we want to maintain a dry bulb temperature of 24 degrees Celsius and a wet bulb temperature of 22 degrees Celsius. Inside the room, there are people and equipment generating both sensible and latent heat. Let's say the sensible heat load in the room is 12 kilowatts and the latent heat load is 3 kilowatts. Based on this, we can calculate the sensible heat ratio as 0.8. Now let's return to the psychrometric chart. Using the SHR value, we can trace a line on the chart that corresponds to this exact sensible heat ratio. This allows us to determine the precise supply air point necessary to maintain the desired room conditions. In this video, I've included a link to an online app that makes it easy to calculate psychrometric properties for specific conditions. The app also provides thermodynamic properties for a variety of fluids. Thank you for watching. If you've made it this far, please subscribe to the channel for more videos like this and visit my GitHub to explore other similar projects.